5 is on volume of similar figures, and basically it's just a continuation of last day. Last day we looked at the following things: ratio of corresponding sides, ratio of perimeters, ratio of areas, and ratio of surface areas, and today we're going to add in volumes. So let's just review first of all. We have two similar figures here. All squares are similar figures, obviously. They have the same shape, a square shape, and they just have different sizes in this case. Let's call this side length here, let's call it A, and we'll call this side length here B. So what's the ratio of corresponding sides then? Well, obviously it's A to B. By the way, just to remind you, another name for the ratio of corresponding sides is the scale factor. Next, what's the ratio of perimeters? So do you remember this from last day? If two similar figures have a ratio of corresponding sides of A to B, then their ratio of perimeters is A to B. It's exactly the same. How about the ratio of areas? It's not A to B anymore, it's A squared to B squared. We saw that last time. And the last thing we saw in our last lesson is the ratio of surface area. So first of all, we wouldn't be able to use these two shapes because these don't have surface area, they just have area. But if we look at these three-dimensional shapes, which do have surface area, and again, if we called this distance here the side length, right there, A, and if we called this side length B, well then obviously the ratio of corresponding sides is still A to B, just like this was up here. But the ratio of surface areas, we learned this last time, the ratio of the surface areas of these three-dimensional shapes would be, again, A squared to B squared. So now we're down to this last case, which we haven't looked at yet, the ratio of volumes. You might be able to figure this out, might be able to think about it. But in case you can't, let's actually do an example. Let's say, we'll use some numbers this time instead of letters, because the numbers can give us a sense of what's happening. So let's say that this side length right here is 2. And this side length here is 3. So if that's the case, then the ratio of sides, or again, I'll just keep saying this over and over again just to hammer it home for you, that's another way of saying the scale factor of these two things is 2 to 3 or 3 to 2, but I'll put 2 to 3. Okay, now we want the ratio of volumes. Well, how do you get the volume of a cube? Get the volume, you go length times width times height, but in a cube they're all the same, the length, the width, and the height. So another way you could think of it is you just take the side length and you cube it, because you're doing a number times a number times the same number, so it's s cubed. So for the first one it would be 2 times 2 times 2, or 2 cubed, and for the second cube it would be 3 times 3 times 3, or 3 cubed. Let's multiply that out. 2 cubed is 8. 3 cubed is 27. Is that in lowest terms? Yes, it is. So originally we looked at the ratio of sides and it was 2 to 3. Now we look at the ratio of volumes and it's 8 to 27. Well, those definitely aren't the same as each other. And it's definitely not this relation, A squared to B squared, because if you square 2 you only get 4. So obviously what is the relation? You need to take the ratio of sides and you need to cube them. 2 cubed is 8, 3 cubed is 27. I mean, obviously that's what we did just right here. So the ratio of volume, if you have scale factor of A to B, the ratio of volumes will be A cubed to B cubed. Okay, if you want it in words like we did last time, it's probably overkill, but there you go. If the scale factor of two similar figures is A to B, then the ratio of the volumes is A cubed to B cubed. Okay. The volume of a cone is V equals pi r squared h divided by 3. What happens to the volume of the cone when the height is doubled? So, originally, a cone has a volume of pi r squared h divided by 3. And we're going to compare that to what happens when you double the height. So if you double the height, well, pi is still pi, r squared is still r squared, but the height is doubled, so you wouldn't call it h anymore. Since we're doubling that amount, it would now be 2h. And you would still divide by 3. Okay, so if we put this in lowest terms, well, you could cancel tons of stuff out here, right? You could divide both sides by pi and get rid of it. You could divide both sides by r squared and get rid of it. You could multiply both sides by 3 and get rid of this. So, you could even divide both sides by h and get rid of that. So it looks like on the left-hand side there's nothing left. What does that mean is actually left there? There's a 1. If you divided by all of this, you'd have 1 left. And on the right hand side, what's still left is 2. So this is what happens when you double the height. Originally, if the volume was 1, then the new volume would be 2. In other words, the ratio of old volume to new volume is 1 to 2. Or another way you could think of this is the volume doubles. So if you had a cone, and let's say that the volume of this cone is 25 centimeters cubed, and then you drew another cone that had exactly the same base, same circular base, but it was twice as high. So it came all the way up to here. What does that mean that the volume would be of that new cone? Well, we just learned the volume doubles, it would be 50. Okay, that's what I was telling you. Okay, next one. What if the radius is doubled? So again, originally, cone has, you can figure out the volume of a cone by doing this. And what we're going to do this time is we're going to double the radius. So pi stays the same, but the radius is now twice as big. It's not r anymore, it's now 2r. And you have to square that amount. Be careful, that's the bit that needs to be in brackets, all that. You have to replace r with 2r and square all of that amount. And then we still have our h and we still have our 3. Again, you can cancel out lots of stuff. The 3's cancel out, the pi's cancel out, the h's cancel out. Don't cancel out any r's yet. What you need to do now is you need to do some simplifying. So I'll just draw like an arrow here to show that what's left on this side is r squared. And what's left on this side, you need to do some spreading the love here. So you get 2 squared, which is 4, and you get r squared, which is, well, r squared. Now you're able to simplify more. You can cancel out the r squareds, divide both sides by r squared. And what that leaves you with, on this side there's nothing, which we know means 1, and on this side there's 4. Oh, okay, so the ratio of old volume to new volume is not 1 to 2 anymore, it's 1 to 4. So the volume quadruples, I guess we'd say. The volume quadruples. And why is that? That's because the radius amount is squared. So if you double that amount and then square it, it's kind of like multiplying by 2 and then squaring, which is 2 squared or 4. Again, if in a picture, if we had a cone, and let's say I had the same volume of 25, but now I draw a new cone that has the same height this time, still goes up this high, but the radius is doubled, so it's wider. Something like that. Not a very good drawing, but you get the idea, I hope. We now know the volume would quadruple in that case. Okay, what happens if both the height and the radius are tripled? So we start with pi r squared h over 3. Pi will stay the same. Tripled, so it won't be r anymore for radius. It'll be 3 times as much, 3r. And we have to square that amount. It won't be height anymore, h. It's tripled, so it'll be 3h. Do you check your phone? That was me again. Sorry. Okay, time to do our canceling. We can cancel the pi's, divide by pi. We can cancel the h, I suppose. Divide both by h. You can cancel the 3's, multiply by 3. Let's see what we have left when we do that. On this side, we still have an r squared. On this side, we need to do our spreading the love. And we will get 3 squared, which is 9. And then r squared, which is, whoops, I forgot to put the dot dot, which is r squared, and then we still have a 3 here. Okay, you can cancel out the r squareds, divide both sides by r squared. What's left on the left-hand side is 1. What's left on the right-hand side is a 9 and a 3, which you're going to multiply, you get 27. Wow. If you triple the height and the radius, the new volume is 27 times as big. Things go up fast when you're talking about volume. So volume is 27 times bigger. Okay, next question. 2 similar statues are different sizes. One's height is 3 meters and the other's height is 5 meters. If the volume of the smallest statue is 216 meters cubed, then what's the volume of the larger statue? Okay, so we have a comparison of 2 statues, and we're talking about height. And height is just an example of a side, right? So we can write down a ratio of sides. The ratio of sides is 3 to, I like to use a fraction, remember, so I can cross multiply, 3 to 5. What this here is, this 3 to 5, this is a ratio of sides, and I know you're getting sick of it, another word for ratio of sides, or another term, is the scale factor. Okay, what we're interested in is, we're talking about volume. So what we want to make here is a ratio of volumes. And we have one volume. It says the smaller one, well obviously that goes with the 3, it's a smaller number, is 216. So you're going to put 216 up there. And this is what we want to know here. Here's our x. So do we just cross multiply? No, because the ratio of sides and the ratio of volumes are not equal to each other. What did we just learn today about the ratio of sides and the ratio of volumes? If you want to take the ratio of sides and make it equal to the ratio of volumes, what do you need to do to these numbers? You need to cube them. That's what we saw today. That if you cube the ratio of sides or cube the scale factor, you'll get the ratio of volumes. So now we can solve this. We will cross multiply, so this is what we're multiplying, and we will get x equals 5 cubed times 216, all divided by the one left over, which is 3 cubed. So that's 125 times 216 divided by 27. And if you do that, it works out to a wonderful number, 1,000. 1,000 what? Well, this was 216 meters cubed, so it's 1,000 meters cubed. The big statue has a volume of 1,000 meters cubed. Great. Okay, the surface areas of two spheres are 36 pi centimeters squared and 144 pi centimeters squared. You know what we mean by the pi sign here, right? This just means, and this happens a lot in grade 11 and 12, rather than actually multiplying this by pi to get the final amount, they just left the pi sign in there. It's a little more accurate, it's a little nicer to work with, especially if when you're doing trigonometry. So yeah, this just means 36 times 3.141 whatever, and this means 144 times that amount. So we want to know if this is the surface area of them, what's the ratio of the volumes? Okay, well obviously we can write a ratio of surface areas. The ratio of surface areas is 36 pi to 144 pi. This is the ratio of surface areas. We can actually even simplify that. There is a pi here and a pi at the bottom, so we can cancel those. And we can divide both of these by 36. Not easy to figure out, but you can actually divide them both by 36. So you'd end up with just 1 on the top, and on the bottom you would get 4. 36 goes into 144 4 times. So what I'm going to do is I'm actually going to move this over. This is our ratio of surface areas. Okay, so is this, but this one's in lowest terms. Okay, now we want to find the ratio of volumes. We don't know how to go from surface area to volume. We've never learned that. But one thing we have learned is the relationship between surface area and sides, ratio of sides. So let's just call the ratio of sides A over B, and let's think, what is the relationship between the ratio of sides and the ratio of surface areas? Well, what we saw last time is the relationship is you take the ratio of sides and you square them, like this. So what numbers must go in here to the A and the B? Well, what squared equals 1? 1. What squared equals 4? 2. So this is my ratio of sides. Again, maybe what I'll do is I'll move this over. Here's my ratio of sides. Okay, actually I'll leave it here. Okay, and what I'll do is this. I will draw an arrow down to show that my ratio of sides is 1 over 2, and I want to write a ratio of surface of volume. Ratio of volume. That's our final question, is we want to know the ratio of volume. So again, maybe I'll put A and B again. What do we know we have to do to the ratio of sides, or the scale factor, to get the ratio of volume? We need to cube them. So the ratio of volume should be 1 cubed, which is 1, over 2 cubed, which is 8. So it's 1 over 8, or if you want, you can write it this way, 1 to 8. The ratio of volumes is 1 to 8. Complicated and confusing and much different than we've done before, isn't it? But it all comes down to those these 5 things right here. This is basically everything you need to know. These 5 relationships right there. It's all we're using in a somewhat complicated way. Okay, cone A is a reduction of cone B with a scale factor of 1 to 9. So there we go. I'm going to write that right away, 1 to 9. And this is the ratio of sides, or they call it scale factor. Same thing. Cone A, so that is the first one, the smaller one, has a volume of 20 centimeters cubed. So 20 goes on the top. We did a question just like this. Don't really understand why I've added this one in here. And we want to know B, so this is what we're trying to do. And we're talking about volume, so ratio of volumes. So is the scale factor equal to the ratio of volumes? No. What do you have to do to the scale factor to make it equal to the ratio of volumes? You need to cube the scale factor. So this is what's going to give you the answer. So x is going to be equal to, multiply those, 20 times 9 cubed divided by 1 cubed. That's 20 times 729 divided by 1, doesn't make a difference. So x equals 14,580. And what are we talking about here? We're talking about centimeters cubed. Probably wasn't necessary to do that question. All right, we did it. We're finished chapter 1, and I believe I did all the videos in under 20 minutes. I'm very proud.
No change, I can change, I